Let's understand this with an animation. Assume that we have a task running, which is the task A, and when it is executing, the system timeout occurs, and now the control is given to the OS because task A's time slot is over. Now OS wants to do context switch. So what OS does now is that it just pends the PendSV exception. It will not do context switching to another task here, but it just pends the PendSV exception. And if there are no interrupts in the system which need to be serviced, then the PendSV handler will run. And inside the PendSV exception handler, the context switching will be carried out. So task B will be scheduled to run. So now you may be wondering that why the context switch operation is done inside the PendSV handler and why can't inside the SysTick handler itself. If you have this doubt, it will be clear now. Let's move ahead. Now the task B is running. Assume that an interrupt occurs. As you know, when the interrupt occurs, processor will start executing the ISR, right? So let's say this is the start of the ISR. And assume that the SysTick is timed out now because task B's time quota is over. So in this case, assuming SysTick exception is a higher priority, processor actually preempts the ISR and it will start executing the SysTick handler. Now, here is a problem. As you know, we have a ISR which is serviced half, isn't it? Now we are in SysTick timer handler, and if you want to do context switch here and return to task which actually a thread mode, then as per the processor design, this is not allowed. Because you cannot come to a thread mode by keeping half serviced interrupt active. So the best way to solve this problem is just pend the PendSV exception here and come back to service the ISR. Since the ISR is active, the PendSV exception will not be triggered unless this ISR finishes, because PendSV is always configured for the lowest priority. Alright, when the ISR completes and if there are no more interrupts in the system, then the PendSV handler runs and the OS will carry out context switching in the PendSV handler so that task A can now resume executing. Great. I hope this animation gave a clear view about the use of PendSV in an OS context switching scenario. Okay, let's move ahead. We can also use PendSV for offloading interrupt processing. As a good design, ISR must be very short. If a higher priority handlers keep processor busy doing some time consuming work, then the other lower priority interrupts will suffer and you may lose the system responsiveness. So that's why the time consuming ISRs usually divided into two halves. The first half is the time critical part and that needs to be executed as a part of ISR execution. Once the first half is done, your ISR will exit. And the second half is called as bottom half, which is basically delayed execution where rest of the time consuming work will be done. So now the question is, who takes care of the bottom half work? The answer is delayed execution by PendSV. PendSV can be used in these cases to handle the bottom half execution of execution by triggering it in the first half inside the ISR. Let's see how it is done. So here I have a task running. Suddenly an interrupt appears and now the processor is executing the ISR. Okay, So you can now make ISR to execute your time critical work first, that we call the first half, and exit quickly by pending the PendSV exception. When there is no more interrupt in the system, the PendSV exception handler will run and it does the time consuming work which we call the bottom up processing. When the PendSV is doing the bottom up processing, it still allows other interrupts to run and it will resume when the other interrupts got finished. In this way, we can avoid blocking other lower priority interrupts because of time consuming work of the higher priority ISR. It surely improves the system responsiveness. Great, that's all I wanted to talk about PendSV exception. In the lab session, I will code and show you how to implement this practically. Thanks for watching.